1, 2, 3, 4. All right, I am back. That was weird. I don't know what happened. I think my browser ran out of cache or something, and then Google Chrome bunged it up. I had to reboot my computer. Okay, but in the meantime, I did look into it, and it turns out I haven't done these questions before. So I feel like I have, but maybe that was a different class. Two cars are moving 97 kilometers an hour, one behind the other, on a rural road. A deer jumps out of the lead car. And its driver slams on the brakes. I wonder if anybody's still in the thing. Oh, 3 people are back. Hi. All right. The driver slams on the brakes and stops. What minimum initial distance between the rear car and the lead car is required if the second car is to stop before hitting the first car? Assume that the acceleration is the same for both cars and the driver for the second car begins braking at 0.5 seconds after the lead car begins braking. So, this question looks really tricky. I'm not going to lie. This question looks super tricky, but it actually is not. So here's the scoop. It takes both cars the same amount of distance to brake. I'll call it BD. Let's see, that's 1, 2, 3, 4, 5, 6, 7, 8. 8 squares. Okay? So, the question is, this car here, the behind car, it's going to wait a couple seconds before it stops. So this guy stops here, and then this guy stops, but a few seconds later. So at some time later, they stop, and then this guy takes, how many was it? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Takes this guy a certain distance, the same amount of distance to stop, because that's what they said. So do the two cars collide is the question. Do they collide? And the answer is dependent on whether this point and this point are further ahead of one another. Because if this point's ahead, this part's behind, they don't collide. Alternatively put, you could draw it as a position versus time graph, and you could say that the first car screeches to a halt. Constant acceleration, so it's a parabola, and then it screeches to a halt. The second car starts out farther behind it, some distance behind, D, travels at a constant velocity for a certain amount of time, delta T, and then begins screeching to a halt. And whether they collide depends on whether these two lines intersect. If the person started out too close, then when they try to brake, they won't brake in time, and they'll collide. If they start out with enough time, there will still be a gap between them, and at the exact minimum amount of time, they will fun. They'll brake at the same thing. Okay, so the long story short, The question here doesn't actually tell us or need to do with the braking distance. The question is all about whether or not how high this line is, say, in the amount of time. In other words, it's whether the car crosses this distance in the 0.5 seconds. In 0.5 seconds, the car is going 97 kilometers per hour. 97 kilometers per hour. Let's convert this times, all right, there's 1,000 meters in a kilometer, so that'll cancel those two out. And there is 60 minutes in 1 hour, and there is 60 seconds in 1 minute. Cancel, 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 cancel. So this tells us how to convert between the two. 97 times 1,000 divided by 60. 26.9 meters per second. Okay. So in delta t is equal to 0.5 seconds, we can move at that speed 26.9 times 0.5. .5 meters. Let me illustrate this with a motion diagram instead, because a lot of you are probably pretty confused. I'll draw two simultaneous motion diagrams. One for the, at t is equal to 0, one for the first car, and t is equal to 0, one for the second car. So the first car starts to slow down. Actually, you know what? Let's line them up so you can see exactly what I mean. So this first car starts here. First car starts here. Okay. 1, 2, 3, 4. 1, 2, 3. 1, 2, 1. Stop. Once you begin the stopping process, let's say it takes this car this far to brake. That's 4, 7, 8, 9, 10, 10.5 units on this graph. Okay. So the idea here is that it takes both cars this distance to stop. This car, though, is traveling with some velocity. So it's going, I don't know, 5 every second. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it's going to travel some distance before it slams on the brakes. 4, 3, 2. Regardless, the second car and the first car both take the same distance to stop. And so whether we're comparing, so in this case, they would have collided, because by the time this guy's still moving, when he runs into the back of the car in front of him. So the question is, how far back do we need to make this distance so that this distance and this distance don't overlap? And to do that, you can see, oh, you know what? There's a thing. I tried this earlier. So in order to keep them from overlapping, we need them to start braking at the same place. Or rather, the back of the car here. So this guy represents the back of the car in front. This guy represents the front of the car in front. The minimum distance they need between them is so that they stop in the same place. Okay. So then the question is, how far do you travel before you start putting on the brakes? And before you start putting on the brakes, you're traveling at a constant velocity. And you know how long it takes before you put on the brakes. So we can combine these two to figure out that this distance is 13.5 meters. And you don't actually need any acceleration information at all. Okay. And nobody's chatting. 4 people are watching, nobody's chatting. Well, that's okay. Next question. Question 45. The day after the incident described in problem 44. Weird. The instructor finds herself in the same situation. This time she tries a harder physics exercise. She keeps running a constant 6 meters per second after drawing even with the bus door and pulls ahead for a while. But the accelerating bus soon overtakes her. By what distance does she get ahead of the door? Weird. Okay, I guess I gotta read the 44 question. As a physics instructor hurries to the bus stop, her bus passes her, stops ahead, and begins loading passengers. I'm a bus. My door is open. I'm a physics instructor. My hair is unkempt. I am running as fast as I can to make it. She runs at 6 meters per second to catch the bus. But the bus door closes when she's still 8 meters behind the door. The bus leaves the stop at a constant acceleration of 2 meters per second. She's Mr. Bus, but as a physics exercise, she keeps running at 6 meters per second until she draws even with the door. I guess I'll draw her in red because she's tired. Calculate delta t, all sorts of things. Okay, the day after the incident, so next day, she finds herself in the same situation. She tries a harder physics exercise. She keeps running 6 meters per second after drawing even with the bus door and pulls ahead for a while. Whoa, way to go, lady. So here's the door. And she's running ahead of it. But the accelerating bus soon overtakes her. What's the maximum distance she gets ahead of the door? I guess I better draw the rest of the bus. So here's the bus. Here's the bus. Here's the bus. So the bus is now accelerating. Wasn't this a fun question to do? Okay. So, what's the maximum distance she gets ahead of the door? I guess to do this we need some equations of motion, right? So let's start our reference frame here. Okay, so her motion is described in terms of being at initial position 0, and she's moving at 6 meters per second. Physics teacher. The bus's equation of motion, it starts at +8 and has 0 initial velocity, and is moving at 2 meters per second. Let me simplify this equation a little bit. Okay, so this is pretty fun. You know what? I'm going to graph these two. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 10, 12, 14, 16. I thought there was a ruler app in here somewhere, isn't there? No, that just moves it around. Maybe that was a different app. Okay, so you're moving at 6 meters per second, starting... Okay, so here's the physicist's trajectory. Oh, wait, I have a ruler somewhere around here. I'll use my ruler. I don't know where it is. Guess I won't use my ruler. Thought I had one. Guess I'll just freehand it. Lord knows how accurate that is. Okay, so the physicist starts there. And every... Oh, you know what? I made a mistake here. I wanted this axis to go up by 1. 1, 2, 3, 4, 5, 6, 7, 8. Every 1 second, she goes up by 6. So, like that. Okay. And then the bus, it starts off at 8. And in 1 second it goes up by 1. And in 2 it's up to... At 2 seconds it's at 12. And at 3 seconds it's at 3 times 17. And at 4 it's 16:24. And at 5 it's 25 plus 33. So 20, 30, 33. Gotta write it down somewhere. All right, 22, 24, 26, 8, 30, 32. All right, so the bus is traveling around a parabola like that. So there is indeed a period of time kind of between then and then where they're in the same place. We want to know the maximum distance ahead. So at each moment, zoom, at each moment there is a distance between them, and we want to know when it's at its maximum. There's a couple different ways you can do this. One of them is you can say the distance between them. You know, I've been using that for a thingy. I'll call it D. The distance between them is, oh no, it's battery pencil's low. Distance between them is do I have another USB connector? No. I have no means of charging this guy up when he runs out of batteries. Okay, well, I guess I better hustle. It's X person minus X bus. And then, so that's equal to 6t minus 8 plus t squared. So we can use this equation. 2 times 4. Actually, you know what? I can factor this equation. So this is equal to oh no, maybe I can't factor it. Anyway, whatever. 2. That's because this is supposed to be a minus sign too. So yeah, so that's minus t minus 4 t minus 2. So that's minus 6t plus, and then that's 8. Okay. So this is a parabola in its own right with intersecting points at 2 and 4. So the maximum point, the distance between them, is going to be the vertex, and it's at t is equal to 3. So at t is equal to 3, the distance is 6 times 3 minus 8 minus 3 squared, which is equal to 6 times 3 minus 8, 1 meter. There's an alternative way to do this, and that's to use calculus. d by dt is equal to 6 minus 2t, so t is equal to 3 seconds, and then plug this in back into d. But that's how you figure out the answer. That's a pretty tricky question, but that's the answer for you. And let's see, what now? Let's see, was that 45? Gross. 47. Calculate using the value of g the time interval required for an object released at rest at some arbitrary point above the ground to reach a point that is to reach the ground calculated using the value g, ground. V initial is equal to 0. I hat. So starting from rest, the initial position is x initial. Oh geez, my pen is fritzing out. This is going to be 1/2. X is equal to x initial plus g minus g over 2 delta t squared. Oh, just be nice. T squared, right? So so you can rearrange this and say when x is equal to 0 at time delta t, xi times 2 over minus g is equal to delta t all squared. Or alternatively, delta t is equal to square root 2xi minus g. Okay, so if g were half its current value, how would delta t change? If g was equal to, There's a couple ways of doing this. Because the pen is running out of ink, I'm running out of time. I'm kind of stressing it out. So let's compare these. T1, G1. G2 is 1/2 G1. Delta T2 is equal to square root 2x1 over algebraic mistake over G2. So that's 2x1 over 1/2 G1. So that's 2xi over G1 times square root of 2. So it's square root of 2 bigger in terms of time. That's your answer. Next question, 53. Why are you guys doing these weird questions out of the book? You're on a second floor building under construction laying bricks of dimension blah. At your command, a coworker tosses bricks up to you and you catch them when they've risen 5 meters above the launch point. He tosses bricks consistently so that untouched by you, they'd rise to a maximum height of 6 above the launch point. Soon you both get good at this and you know exactly how many seconds to yell 1, 2, 3, throw. And you reach out and catch the brick on its way up. What length of time interval if your throw worker throws without dividing your command? Oh, jeez. Oh, man, that's bonkers. Okay. So. She's running out of time here. Oh, you know what I can do? Hold on, I'm going to switch mics and then... No, wait, I don't have another cord. Yes, I do. Okay, hold on. This will help with panic. I'm going to switch mics to my crummy mic, and it's your own fault for giving me these long-ass questions to do. Alright, hold on. Okay. There. Click. And then this guy. And I can't. Okay, there you go. Thank you for the note. Okay, so you can calculate the initial speed of the brick down here. And then you can even figure out how much time it takes to get to the top. V is equal to V initial plus AT, so it's 10.8 minus 9.81 T. T top is when V is equal to 0. So it reaches the top of the arc at 10.8 minus 9.81, so it's 0.99 seconds. The original question said, how much this time? And to figure that out, I'm going to go 5, okay, initial position, 0. Initial velocity, plus 10.8 meters per second times time, minus 9.81 over 2 times squared. So at time is equal to delta t, x is equal to 5. Let's go with that. 10.8 times t minus 9.81 over 2. I guess that's delta t. Delta t all squared. And you just solve this equation using the quadratic formula. And that should be enough to finish the question. Oh, is there still no audio? Hold on. Yeah, no, there should be audio now. It's on a delay. Yeah, okay, we're cool. Let's try the next question. 71. A ball is projected vertically upward from an initial position 5 meters above the ground. The same instant a cube is released from rest down an ice-covered incline from a height not necessarily equal to 5 meters. The two objects reach the ground at the same instant. Both have the final speed of 15 meters per second. What's the angle of the incline? Oh, that's funny. Oh. Good-o. Good-o. Okay. Okay, what's the angle of incline? Okay, so, and it says a cube is released from rest. Oh, that's funny. Oh. Okay. So let's go over this. Final speed, FYI, it depends on your initial height. Why does it depend on your initial height? A couple reasons we could explain it. One of them is gravitational potential energy. But the idea here is you throw the ball. We don't know how fast we throw it up, and we know how high it starts. We don't know what time it reaches the ground, but we know how fast it's traveling when it reaches the ground. Oh, who's that? Oh, it's my wife telling me she misses you. Me. I miss her. I miss you too. but physics calls. Okay, so we don't know how much time it takes for the ball to go up and come down, and T final. And we don't know what V initial is either. And you don't know how much time it takes for the block to reach the bottom. T final is equal to question mark. And you don't know what the acceleration is. And you don't know what the Y initial is. And you don't know what X initial are. There's just a ton of these things you don't know. But this is actually a pretty cool question. Dig it. This is a one-dimensional motion problem. And so if I knew, because of how it's described, if I knew how long it took to go to the bottom, I could figure out what the acceleration is. And if I knew what the acceleration was, I could A sine acceleration is equal to G sine 20 of this sucker and figure out what the angle is. So the question is, how long does it take for this ball to reach the bottom? Good question. To figure out how long this ball takes to go up and come down, you need to figure out what VI is. Except we can't. But we do know is the final velocity. And so we can kind of use this we can use this equation, for instance. You know it's falling under gravity, so 2a T final minus T... Oh, geez. Right. I'm running out of pen. T final minus... No, they're x's. Your hand was right. Your mouth was wrong. X final minus X initial is equal to V final squared minus V initial squared. 2 minus 9.81. Final plot is 0. Oh, right. Reference frame. In this one, let's say that this is x is equal to 0, and let's say this is increasing. All right. So your final position is 0. Your initial position is 5, right? 5 meters above the ground. Oof, that was weird. Your final velocity, or your final speed is 15 squared. And we don't know VI squared. So I can solve for that. 15 times 15 minus 2 times 5 times 9.81. So that's V squared is equal to 126.9. V initial square root of that is equal to 11.2. And then I can use this to figure out how much time it took. Because V is equal to V initial plus AT. Your final velocity is minus 15. Your initial velocity is 11.2 going up. So T, the amount of time it took to get to the bottom, is minus 15. It took 2.67 seconds. Okay, now this one. It's a one-dimensional motion problem, so I'm going to start... Wait, I don't know its initial height. Gross. Okay, well, let's just let's work it through. I don't know where that is, so I'll say that's x equals 0. And here, let me draw a nicer picture. So, x is equal to xi, 0 initial velocity, plus a over 2 t squared. And v is equal to v initial plus a over 2. No, there's no over 2. A t. Your initial velocity is 0 in this one. So, I know that at t is equal to 2.67 seconds, my velocity is down slope with velocity 15. I guess it's minus. So, minus 15 is equal to a times 2.67. So the acceleration has to be minus 5.61 meters per second squared. And like I promised, minus 5.61 is equal to minus 9.81 times sine of theta. So sine of theta is equal to 9.81. So theta is equal to arc sine. Answer 34.9 degrees. Thank you very much. Here's a picture of a bunny. I have just done physics online for 3 hours straight, minus technical difficulties. So the next time you complain about doing physics for 3 hours straight, at least nobody can watch you make mistakes. Alright, see you later.